Hello, so in this video, we are going to go over basic PyTorch for NLP. So the target audience of this video is someone who's done projects in PyTorch before regarding NLP, but maybe doesn't have the greatest foundational understanding of what's actually happening. Maybe you've encountered some errors before, figured out how to fix them without really knowing why those errors occurred. So if that describes you, this video is for you. Um, as always, this presentation was created by myself, Darian Lee, and my coworker, Yujia Ching. Okay, so first we're going to start by talking about data in tensor types, as well as visualizing common NLP tensors and reshaping. So you may have come across errors about conflicting tensor types. So something like a 32 floating point, a long, a 16-bit, and so on. And we're basically going to talk about what those actually mean. So when representing numbers in a computer, they are stored in this format below, where you have different bit amounts representing different storage capacities. And you always are going to have 1 bit allocated for the sign, which is whether the number is positive or negative. You're going to have some amount of bits allocated to representing the exponent, and the rest of the bits representing the mantissa. So basically what this means is if you think about like scientific notation, how you can write something like 3 times 10 to the -6 or something like that, we can kind of do the same thing in binary using base 2. So we might find out that we can represent a number as something like 5 times 2 to the 7 or something, and that would kind of be the exponent being the 7 and the 5 being the mantissa, and the sign in this case being 0 for positive. However, it is going to get a bit more complicated because everything is going to be represented in binary, and there's going to be a bias added to the exponent, but I will get into that in the next slide. So let's say we want to represent something like 85.14 in float 16. So we already know that we need to allocate 1 bit for representing the sign. So in this case, the sign is positive, and if we go here, we can see the sign is represented as -1 times the sign. So if we want to represent a positive number, we're going to actually make this sign zeros, because -1 to the power of 0 is 1. Okay, so we've gotten the sign figured out. Now we got to figure out what the exponent is and the mantissa. So the exponent you can essentially think about as how many 2's can go into this number. And this is actually really easy in binary because once we write 85 in binary, we can just count the number of digits because these digits represent factors of 2. So we can see that the actual exponent in this case is 6. But so I think this is going to sound confusing at first, but once I explain why we do this, I think it will make a lot of sense. So in float 16, we're actually going to add a bias of 15 to the actual exponent. So we're going to, instead of 6, we're going to get 21. And the reason why we do this is because if you think about storing bits in a computer, we don't want to have to waste a bit on defining whether or not it's positive or negative. So what this essentially does is it shifts everything up by 15. So if you originally had like -15 as your exponent, you now have 0 as your exponent. And it allows us to save that extra bit. And it won't actually impact really anything, because when we decode, we subtract this 15. So don't be worried about this. It's just there to save space in our computer. Yeah, exactly. So now how do we get the mantissa? So essentially what we're going to do is we are going to represent both these things in binary. we are going to put the little dot between them. Then we are going to just convert this into the normalized format, which is some number times 2 to the 6, which is going to equal this thing that we found. And the mantissa is just going to be the part after the decimal point once we convert it to this form. So we're going to end up with a mantissa of this, the exponent of this, which is 21 in binary. I don't remember exactly what number this is in decimal, but yeah, you can figure that out on your own if you are curious. And something interesting about this is, oh, and this is how you can think about it being represented. -1 to the power of sine, 2 to the exponent minus 15 times 1 point, and then the mantissa. And the interesting thing is that when we convert it back to decimal, it's not actually fully exact. So remember, our original number was 85.14. When we convert it back, we get 85.125. So the lower amount of precision, the lower number after the float, the less exact our actual storage of the number is going to be. So you might have seen some errors about needing a long tensor um, in certain areas. So long tensor is actually the int64 type, so we're using 64 places to hold it. And if you've ever gotten errors about a certain type being expected, or you can't do things with two floats of different types, it's just because they're stored physically differently. So you run into areas where a certain function was made um, to work with a certain type of these numbers, and if you give it an incompatible one, it might break down. Okay, so now we are going to get into tensor visualization for NLP. I found this image on the internet, which I think is really cool for showing how you can visualize high-dimensional tensors. But for NLP, we're really going to be focusing on this 3D tensor. We don't typically get into 6D stuff, unfortunately. So, if you've been in any sort of NLP class, you've probably seen this drawing of batch size by sequence length by embedding dim. And it's usually represented in some way where you have each of your sequences for the batch. So in this case, I have 4 sequences of length 3 in this batch, and I have an embedding dim of 4. So these are the embeddings of all the words for all the sentences in my batch. However, I think this can sometimes cause confusion because if you've done an NLP task, you know that each of these words are going to be encoded. Then you also have the embeddings, and you might think that somehow these encoding words are still present in the diagram. Like we have 1, which is I, which corresponds to this vector. We have 2, which is love, which corresponds to this vector, and so on. However, this isn't exactly accurate, and it might make it harder to interpret tensors in code. So the reality is going to look more like this, where the only numbers present in the actual code are just going to be the embeddings, and you can just think of it as stacks of embeddings for each sequence. And I think once we start thinking about it in this way, it will make it a lot easier to understand what we're actually seeing if we print out a tensor. So, for example, if we have this tensor and we print it out, we are going to get the batch, then we are going to get the 2 sentences in the batch so far. Then we're going to get, in these sentences being I love tigers and rah rah rah, we're gonna get 3 little lists in here, which represent the embeddings for each word. And these are going to have a size of 4, which is our embedding dim. So we can see we have I love tigers, embedding for I, embedding for love, embedding for tigers, and so on. And this is just in general. We're going to have sequence 1, sequence 2, sequence 3, sequence 4, then the embeddings for each position, and these inner vectors are going to be the embedding dim. As you can see, I really kind of simplified the quantities we're working with. If you've ever worked with NLP, you know these embedding dims are going to be a lot larger, but I think it makes it a lot simpler when we show them as only being 4. Okay, so here's a little quiz. You can shout it out at your computer. So what are the dimensions of this tensor based on what we talked about? I don't know why it changed to white, but yeah, so we're gonna get a dimension of 2, 2, 3 because we have 2 sequences in the batch, which are the orange things. We have 2 tokens per sequence, the green ones, and an embedding dim of 3, which are these little numbers here. Okay, so what if we did want to explore higher dimensional things? How could we think about that? So we could think about it as maybe we want to focus on multiple batches at the same time. I don't know why you would do that, but in this case, you just have the same batch size, sequence length, embedding dim, and you would also have like 4 batches. Um, So essentially, we would just be adding more brackets. Like we'd have the brackets for batch 1 and then the brackets for batch 2. Then the same things would be inside of them. An area where this actually does come into play is image processing. So when you're processing an image, you typically have the image height, the image widths, and the number of channels, as well as the batch size. So this would be a case where you would actually want to look at 4D tensors. And here is a zoomed in cross section. I don't know why I included that, but it's there. Yeah, so now we're going to go into reshaping. So, you've probably seen this particular reshaping function before, which is if we're calculating the loss, we're gonna do view, and we're gonna do -1 to vocab size, and we're also gonna do the same thing to target. So this you pretty much have to do anytime you take a loss, and if you've done any NLP project, I'm sure you've encountered this before, but you might not know what is actually happening. And I just want to say real quick, I think this is really good to know because I think a lot of people are scared to reshape their matrices. When you don't have a good, solid understanding of what's going on, um, you might get an error that can be really simply fixed by just reshaping your matrix, but you're going to be so scared to do this because you're not going to know what the reshaping is actually going to do. You're going to worry that it's going to mess something up. So I think this is a really important section to pay attention to. So dot view is going to change the dimensions of a matrix. So for example, if we have a tensor called A with shape 222, and then we view it to 10.8, it's going to convert it to the shape of 10.8. But this is only going to work if the product of the dimensions are equal in both matrices. So in this case, they both equal 80. Now, why is this the case? It's the case that you can think of the product of these dimensions as how many things you are actually storing in the tensor. And in NLP, these things are typically embeddings. So it's how many actual embedding numbers are in the tensor. All we're really doing is rearranging where they are, but we're never adding or removing any when we're reshaping, and that's why it always has to be equal. Yeah, I have a little. So let's say we have tensor A with this shape, and we want it to be a 2D tensor with the last dimension as 40, but we're not sure what the first dimension should be. In this case, we can use -1, which will calculate the first dimension for us and output to 40. So all this is essentially doing is, if we have -1 here, we have 40 here, it's just going to divide the product by 40 and get 2. Okay, so this is how the reshaping actually looks for something like this function above, where we are using view in order to put our outputs in the same format that the loss function expects. So here we know that our second dimension is going to be vocab size, which here, let me annotate, which is going to be 4, both here and here. And we're putting -1, which we already uh, talked about, which is just letting it figure out what the other number should be. So it's going to divide the total number of elements, which is 4 times 3 times 2, by 4, and it's going to end up with 3 times 2, which is 6. So this other dimension is going to be 6, and it's always going to be the batch size times the sequence length. So I drew out kind of what's happening here, but you can think of it as the first token prediction logits for this first sequence are going to be here now. In the second token prediction logits for the first utterance are going to be here now. So it's essentially just you're stacking all the sequences from all the you're stacking all the tokens from all the sequences vertically in a stack. So instead of having I love tigers, rah, 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 as different sentences, we're just going to have a list of tokens in all our sentences going down. And that's what this represents. And these are going to be the logit probabilities of every token in our vocab that we're trying to map up to these individual tokens. Um, so yeah, so exactly. So the argmax of this row is going to be the predicted token for sequence 1 index 0. Same with this one, it's going to be sequence 1 index 1. And we're gonna do the same thing to targets. So targets are gonna go from batch size sequence lengths to batch size time sequence length. So the targets are also going to be made into this vertical, like just each token stacked on top of each other. So let's say our vocab size was what, question mark, who, how. So we have 4 things in our vocab. This is what they are. And this is what our targets are after we reshape them using view to -1. So essentially what we're doing here is this row is going to contain all the logits for the 0th index of that sentence, and this is going to be compared to the target, which is what? In same here, for these are going to be all the logits, which are the predictions for the first index in the 0th sequence, and this is going to be compared to the target, which is question mark. So as you can see, this is basically only done for efficiency reasons. It's a lot quicker to deal with this 2-dimensional matrix than it is to deal with something in 3D. So it's essentially all we're doing is we're collapsing everything into 2D, and then we are comparing them on a token by token basis. And this is going to work for the loss, right? Because we just want to see, like, given all these tokens we were supposed to predict, how close were we to those tokens. Okay, so we have another little quiz question. So given this A, which is currently of dimension batch size 2, sequence lengths 2, then embedding dim 3, so 2 by 2 by 3. What is gonna happen if we try to reshape it to be 4, 3? So you can maybe pause the video and try this on your own, but essentially we're just gonna get this. So this is kind of showing what happens in code, but essentially all we're doing is we're just removing these brackets which define the batch. So once we remove the brackets, we're just gonna have just all these sequences here, then all the embeddings inside. So this is going to be of size 4, 3 because we have 4 sequences and 3 embeddings. Yeah, so all you're doing is adding or subtracting brackets. Okay, so squeeze on squeeze. So let's say we had A as a torch tensor that looks like this. So we can see that this is batch size 1, sequence length 1, and embedding dim 2. But let's say we want to collapse this into a smaller dimension. So one thing we can do is a dot squeeze, which is going to remove all dimensions of shape 1. So the output of something like this is just going to be this 4, 5. So it's removed all these extra brackets, which we're adding dimension of 1. If we do a squeeze with a certain index, it'll remove the dimension of shape 1 at that index. So this only works if the dimension is 1. So in this case, it's going to remove these first brackets up here. We can also call unsqueeze to add a new dimension of 1 at that specified dimension. So this is essentially just adding another empty thing of brackets outside the thing we're putting in. So if we unsqueeze that 1, we're just going to add, where's my annotation? I don't know how to annotate. Oh, here we go. So yeah, we're just going to be adding those little brackets. Okay, so some other reshaping functions. So first, actually, I don't know if I talked about reshape yet, but you might be wondering, like, oh, we're talking about view, but I've heard about something called reshape. What's the difference? The answer is that they are essentially completely similar. The only difference is how they are stored on the computer. So I believe, do I talk about it here? I guess I don't, but essentially, the only difference is one of them, if they both happen to be stored continuously, there's no difference. But if somehow the tensor is stored non-continuously, reshape will create a copy. No, view will create a copy of that tensor, which is stored continuously, and reshape, I think, will just cause an error. But it doesn't really happen that often, so in most cases they're completely interchangeable, but yeah. Okay, so other important functions to know is transpose permutate. So essentially this can just switch the dimensions around. So yeah, so exactly. So you can take something of shape 2, 3, 4, and you can make it shape 2, 4, 3. And once again, this isn't going to be changing the actual values, it's just going to be changing the order um, in which they occur. Actually, no, it's not even going to be changing the order, it's just going to be changing the groupings. So stack, you're going to essentially stack 2 different tensors along a new dimension. So if A has shape 2, 3 and B has shape 2, 3, then stacking them will add this dimension, which will be like tensor A's here and tensor B's here. And yeah, this is often used in the collate function. The first one is typically used when you're calculating the dot product of a tension. And concatenation, I think this is pretty simple. You probably already have a good handle on this, but essentially you're just combining the tensors on a dimension. So you can think of stack as like you have two tensors and you're just kind of forcing them together, but kind of as their own separate things with brackets around each of them. Whereas concatenation, you have some tensor and you're just adding something, like combining it to the end of the tensor without brackets separating them. Uh, I don't think we are actually gonna do the Kahoot since it's YouTube and that would be weird, but yeah, that would be the end of the presentation.